You got a little preview. Okay, hello everybody. I am Sophie, and I'm going to talk to you about a mission concept called Vector. So I am with the WashU Satellite group. We are a undergraduate student-led group at WashU, whose mission is to design and build real spacecraft. So we were founded about 2 years ago, and we are now about 60 members strong. We are currently working on 2 missions, a WashU CubeSat that will launch next year, and a high-altitude weather balloon mission that will launch this December. But I'm going to talk to you about a very future mission concept that I worked on over the summer called Vector. So from our previous work on a high-altitude weather balloon mission, we came up with an idea for a 3U CubeSat. And so as you do, if you're a university team, the first thing you do is you try to find money. So we submitted a proposal to NASA's CSLI with our idea. Unfortunately, this was not the year to submit anything to NASA. CSLI was indefinitely postponed. But this was a great opportunity for us to look back and reflect on what we had submitted. And we realized shortly after that we had submitted an idea, not a mission concept. We hadn't done any feasibility analysis, we hadn't made any budgets, mostly because we didn't know how. But luckily, we also submitted a proposal to the University Nanosatellite's Mission Concept Program. We were accepted into that, so UNP is actually broken into 2 parts. It's more well-known for its 3+ year program that helps student university teams take their mission concepts and take them all the way to launch. But after doing this program for many years, they realized a lot of the proposals they were getting were actually ideas, not mission concepts. And so they created a summer-long program for people like us to take our ideas to concept. And so that's what I was a part of over the summer. So me and a couple other interns went to Albuquerque, New Mexico to develop Vector. We actually had a week-long kickoff in Kennedy Space Center where we had a crash course in mission design and everything satellite. So great learning opportunity for all these university teams out here. We also got to tour the VAB, so that's me in front of the Artemis II rocket. Had to throw that in there. So over the summer, essentially we took Vector as a proposal and turned it into a final mission concept. We went through a mission overview presentation, a system concept review, system requirements review, all with NASA and DoD experts. Eventually, in the end, we got to a system requirements spreadsheet, a mission design document, and all of our budget sheets filled out. Of course, this wasn't a linear process. My presentation today will be pretty linear looking, but I want to remind people that it's 5 steps back, 5 steps forward, 3 steps back when you're making mission concepts. So now to actually get into Vector itself. This is an astrophysics mission, so bear with me, you're going to have to hear some science. So gamma ray bursts, these extremely energetic events in our universe, they come from supermassive stars going supernova and collapsing into black holes, or neutron stars merging together, so these high energy events. And they produce these jets. If you can see on the left picture, these 2 jets coming out. If we zoom into that, we can see the evolution of the jet. Looking closer at this picture, we notice that it's broken up into 2 phases. We have the prompt emission phase and the afterglow phase. The prompt emission phase happens first, and that's where we see those initial gamma rays. In the afterglow phase, we also get more gamma rays, but we also get light in all different sorts of wavelengths, so you can see visible light here. But after studying these things for so long, astronomers started to notice that actually we get visible light that shows up in this prompt emission phase as well, called prompt optical emission. And this visible light's important because it's actually inside the jet itself. So this is how we can study what the jet is made of, and it's really close to the black hole, so we can study that really well too. So we want to capture that visible light. Notably, it looks like a new point source in the sky, so like a new star or something just appeared. But this actually happens really quickly. This prompt emission phase lasts for seconds to minutes. So if you want to capture this stuff, you have to be fast. So our scientific need is if we have a detector and it captures a gamma ray burst, then we want an optical telescope to capture that visible light within seconds to minutes afterwards. But let's add some more to this problem. Detectors often have a wide, localized region where they know the burst came from. Optical telescopes, on the other hand, often have smaller field of views and have to search through this region to find the burst. For that reason, the development, testing, comparison, and validation of search algorithms for the detection of these transient events is of interest, especially in real orbital environments. Okay, why orbital, you may ask? Well, of course, people have tried to work through this problem before. ROTC was a ground-based observatory that attempted to capture these transient events. However, of the detections that they got, they only managed to capture about a third of them. And even then, their imaging pipeline wasn't great, mostly because of weather and their location on the Earth. So we thought, why don't we put this on a CubeSat? So, just to recap, we want to capture these prompt optical parts of gamma ray bursts. To do this, we have to perform searches very quickly. Doing this in space can be faster, better, potentially cheaper. But first, we actually need to figure out if searching for transients is even viable to do on a CubeSat. And catching these real bursts is hard. We don't actually want to depend on that for a technology demonstration. And for that reason, we want to figure out a way to, have our search be reliable every time. So we decided to figure out a way to make an artificial transient. In order to do that, we figure out the regions that Vector will see when it's in space. We then make a copy of that region on the ground, and then we remove a star from one of those copies. We now have an altered region star map, so if Vector looks at this place in the sky, it's going to see a new point source that appeared, just as if a transient had suddenly popped into existence. So from there, we defined our mission. So on a CubeSat form factor, we want to demonstrate an optical telescope with onboard processing to perform search algorithms. So we're capturing astronomical images and using onboard processing to detect transients. So we came up with two experiments. Our minimum experiment, just to test this out, is to test out comparison algorithms. So again, we have that altered region star map that we're now going to load onto Vector on the ground. And we can put as many of these as we want on Vector. Well, as many as our data can handle. And then we get into orbit, and we tell Vector to look at some place in the sky. And Vector determines when it will see that location and store that information. And then at the time of observation, it will slew into position, and it will actually take a picture. And then it will run a basic comparison algorithm on board to try to see if it can find the missing star. To actually take this one step further, we decided, we want to actually be able to search a larger region as if we were looking for a burst. And so here's our full experiment where we have a larger region that we search through until we find a star. Yay, we found it. Okay. So then after this, we did a lot of feasibility analysis over the summer. To do that, first we had to pick out some preliminary components. So our payload is a COTS Canon lens and a scientific-grade CMOS sensor, as well as a Raspberry Pi. And then for our ADCS system, we used their Clyde Space ADCS, a GPS, and a sun sensor. And then we chose an S-band patch antenna for our comms. And as you can see, we went from a 3U to a 6U very quickly to fit all of these components. So this is our volume budget, all laid out in a 6U. For our pointing budget was also a very big concern because we want to be able to pretty accurately point at these things. So we had a 2 arc-minute pointing requirement for our mission, and taking into account all of our errors from our ADCS, our positional knowledge, mechanical alignment, and thermal error. We were within that 2 arc-minute requirement. As for our torque and momentum, we have a max slew rate of about 1 degree per second using this ADCS system. We also did a power budget by first breaking Vector into different modes. Notably on this, I wanted to put this up because we do experiment in eclipse. For that reason, there's thermal concern from our sensor getting too hot if we were not in eclipse. And the sky is darker in eclipse, naturally. And so we could be able to see things to a greater illuminating magnitude. But looking at our energy balance over time, doing both experiments, we never get below the watt hours that would be detrimental to our batteries. We also did some basic simulation work to actually simulate the images that we would see on board. So by putting in all the specs of our sensor and imager, we could figure out actually what images would be outputted to what illuminating magnitude. So in conclusion, the future of Vector, what does that look like? As I said, we have 2 other projects. So our 1U is to build flight heritage at WashU. It's also got a pretty cool controls payload on board that my colleague Jesse will be talking about tomorrow. And ERIS is our high-altitude weather balloon mission, which is trying to detect these optical counterparts of gamma ray bursts. So this gives us optics experience and helps us develop the science. Combining these 2 missions together is how we get to Vector. And so we do plan to eventually submit a proposal to this longer 3+ year program and take our concept that we developed over the summer all the way to launch. So with that, I'd like to thank you and see if anyone has questions. Also happy to talk about the mission concept program if you have questions about that too. Thank you.